I want to tell you just a few introductory remarks about the Center for Macular Degeneration and why we're so excited about ophthalmology research here in 2009. When I was in medical school and graduate school in the late 70s and early 80s, genes were just starting to be manipulatable. We just started learning how to isolate them and understand them and sequence them a little bit. And we and a number of others imagined that one day, by having this ability to study genes at that level, that it would somehow make a big difference in the way we could take care of patients. But I must say we had a pretty naive understanding about how that would work. You know, it was sort of like, there was this, I have this great cartoon that I show a lot in talks, and a scientist is up here on the blackboard, and it has two words, gene and cure, and it has an arrow going from gene to cure. And a person in the audience says, "Excuse me, would you be a little bit more explicit in step 2? And so that's the thing, of course, right? How do we go from that gene to the cure? But in the last 25 years, a number of genes that cause human blinding disease have been discovered, many of them here at the University of Iowa. In fact, this institution is the world leader in genetic eye disease. And we are now getting a much clearer picture of how that's going to work. And I'll just give you an overview of that. Basically, genetic eye disease ranges from very common diseases like age-related macular degeneration that you've heard of, that affects 1 in 3 people over the age of 75. And now that the rest of medicine is so successful in protecting us from heart disease and cancer and stroke, the average person in this country lives well over 85 now. And many people live very productive lives up into their upper 90s. And so that's the great news, but then it unmasks some of these other diseases like age-related macular degeneration, threatening these otherwise healthy patients with blindness. So 1 in 3 people over the age of 75. We now know that this disease is largely genetic. That is, the predisposition to it is genetic. And the way we think that genes are going to help us cure that disease is analogous to the way lipid testing or blood pressure testing helps us prevent heart attack and stroke. That is, we're going to predict the future. We're going to use genetic testing to tell who is at risk for losing vision when they're 20 or 30 or 40 years old, and then treat them in ways that will keep these little drusen from forming in their retina, so that we'll push the onset of the disease that they would have had back to age 105 or something like that and protect their vision that way. At the other extreme, though, there are diseases, very rare diseases that cause blindness, maybe in only 4 people per year in the United States, something like that. These are incredibly rare conditions, but there are hundreds and hundreds and hundreds of them. And so together, they affect millions of people in the United States. At that end of the spectrum, where something is really severe and you might be born blind, or you might be born with something that would make you blind before you're 20, there are going to be interventions in which we will actually go in and put a new gene into the retina to replace the missing gene, and therefore either restore vision to the blind child or prevent them from going blind. And the first treatments of this type just began last year in the United States in 2 groups, one in Gainesville and one in Philadelphia. And all the patients in those 2 studies were genetically tested here at the University of Iowa in the Carver laboratory. So the other kinds of things that are going on is a lot of patients who have either macular degeneration or retinitis pigmentosa have already had a lot of damage to their retina, like our friend Leo now. If he was looking at himself in the mirror, would see about this much of his face as he's trying to shave in the morning, and that's pretty frightening to him and pretty frightening to those of his friends who watch that change in him. But now we're imagining being able to use stem cell technology to actually harvest cells from Leo himself and teach them to be photoreceptor cells and put them back in the retina and convince those cells that this is a new retina being built and have them wire up to the bipolar cells and ganglion cells that are there to restore some of his vision. Very similar things like that are underway for macular degeneration. And then for people in which there's just an enormous amount of injury at the level of the photoreceptor cells, and there really isn't a way to overcome that with stem cells or gene replacement therapy, scientists are working on something that the best way I could describe it to you is a cochlear implant for the retina. It's an electrical device with a little planar electrode array that will be actually implanted on the surface of the retina and carry a signal from an external camera to the optic nerve and restore vision to people that are completely blind from some of these diseases. And 3 different companies are within 18 months or so of being able to deliver those devices to scientists for us to be able to start experimenting with providing those to patients and figuring out which patients would be best for those. So here at the University of Iowa, we're engaged in all of these different types of research that I've told you. It's so exciting for us to have lived through the period of investigation in which we imagined these things happening, and now we are standing right at the edge of these things happening right here in Iowa City, and we're in a leadership position, and largely because of the incredible generosity and leadership of many of the people in this room.